So this is chapter 15 in the Zumdahl book. This is unit 7, chemical equilibrium. And I'm going to use something from Prentice Hall here that has been significantly modified. Now, if you look at the two arrows on the screen, you'll see the one you're used to going from left to right. You'll see one going from right to left. Because some, in fact, most chemical reactions are reversible. That is, reactants become products, but some of the product can turn back into reactants with a different direction. So that's what we're going to talk about really for the rest of the year. We've encountered it in the last unit when we were talking about reaction mechanisms. We saw that NO reacts with Br2 as step 1 and sets up an equilibrium to form what I call NOBR2. And the NOBR2 can fall apart into NO and Br2. That equilibrium sets up quickly, and it sets up step 2, which produces 2NOBr. Now, in equilibrium, whenever an equilibrium is set up, as you see in these reversed arrows, the rate of forward is equal to the rate of reverse reaction. This can be shown with simulations. If that's the case, then the rate of forward reaction is K1 times the concentration of NO times the concentration of Br2. But the reverse rate and K's are not the same. K in the reverse direction is just multiplied by the concentration of the NOBr2. But these two expressions are equal. If we solve for the NOBr2, we get K1 divided by K minus 1. In other words, we just divide both sides by K minus 1. And that gives us the formula for NOBr2. We could also write it as K1 over K minus 1 is equal to NOBr2. We divide both sides by both of these reactant concentrations, and so we see now they're in the denominator. So K forward divided by K reverse is equal to the concentration of the product, left to right, divided by the concentration of the product right to left, which is the reactant left to right. This is going to be an important expression. Now, you can see in it reversible dimerization, and I have linked that on the learning guide, or excuse me, the lesson plan, and the revised agenda for the day, where two molecules of NO2, which absorb light so that the whole thing looks red, will, in a dimerization reaction, they will collide with each other and form N2O4, which doesn't absorb visible light. And as you can see, hot water, cold water, the temperature affects what is predominant. Here, in hot water, the NO2 is predominant, and here in cold water, the N2O4 is predominant. So, the concept of equilibrium. Chemical equilibrium occurs when a reaction and its reverse proceed at the same rate. So here you see in very cold water, this is probably dry ice here in acetone, extremely cold. We're down getting next to close to 100 degrees negative Celsius. And as you can see, nearly all the molecules are N2O4. As you warm it up, the forward reaction, or the reverse reaction, goes to NO2, and you get some of these break up into NO2 molecules. And when you get much warmer water, you see not a whole lot of N2O4, quite a bit of NO2 in the mixture. So you can affect equilibrium by temperature, because what affects rate? Well, if you're not changing concentration, the temperature can affect the rate. So as a system approaches equilibrium, both the forward and reverse reactions are occurring. And they continue to occur once they reach equilibrium. Once equilibrium is achieved, the rate of forward and reverse reaction is equal. The forward and reverse reactions proceed at the same rate, so it looks like nothing is happening. You can't tell a difference in the concentration or partial pressures of the two from moment to moment. It stays the same, but the reactions are still occurring. Now, will the concentrations be equal? And the answer to that question, of course, is that once equilibrium is achieved, the amount of each reactant and product remains constant, but they're probably not the same. As you can see here, equilibrium is achieved, and you have, at that particular temperature, you have this amount of N2O4 and this amount of NO2 in the reaction vessel. So, a system at equilibrium has equal rates and constant concentrations of reactant and product, but the concentrations are almost certainly not the same. Once equilibrium is achieved, you have equal rates forward and reverse. You have constant concentrations or partial pressures of reactants and products, but those concentrations are almost certainly not equal. So, depicting equilibrium. In a system at equilibrium, both the forward and reverse reactions are running simultaneously, and that's where we get the double arrow. N2O4 is breaking up to the 2NO2, and NO2 molecules are colliding to form the N2O4. All right, we're going to have a little digression here because we need to make a comparison or contrast with what goes on in a biological system. You recall from biology the term homeostasis, and it's the maintenance in a living organism of a constant internal milieu, even if the external environment changes. So, for instance, if things get real cold in your body, then the muscles start to shiver and they're using up potential energy coming out of maybe glycogen, or if there's glucose flowing around in there, or even fats. You get the metabolism speeding up, so and you get the muscles contracting so as to increase the temperature of the body. That's homeostasis working on temperature. On the other hand, if you get real hot, you begin to sweat, and the liquid, mostly water, evaporates from your skin. That, as you remember, is a process that involves transferring energy from the skin to the water. The water evaporates and takes that heat away because the gas, the vapor, has a higher potential energy than the liquid. So, another way organism chemistry adjusts, your CO2 level in your blood has to stay pretty much constant. There's very little fluctuation in that, and you have a chemistry that adapts to make that happen. We'll see when we get to buffers some of that working in your body. Now, homeostasis then mimics equilibrium, because remember, in an equilibrium situation, there is no change in the concentration or partial pressures of reactants and products. But homeostasis requires a constant input of energy and supply of nutrients and excretion of waste, or the organism dies. Therefore, homeostasis requires an open system, open to exchange of heat, exchange of chemicals, and so forth. But equilibrium systems are closed systems. You saw the diagram of the NO2, N2O4 equilibrium. You saw a closed vessel. Nothing comes in or goes out. Now, heat can come in or come out, but then with a change in delta H, of course, you know that you will change the equilibrium because you will speed up whatever the endothermic reaction is. Okay, so steady state and homeostasis. Homeostasis refers to the entire internal environment. The term steady state can be restricted to describing specific mechanisms. A cell is in homeostasis because every mechanism that keeps it alive is in a steady state. So, for instance, when you have an animal cell, you have the mitochondria taking the glucose and pyruvic acid and giving you ATP so that other processes in the cell can keep going on. That's a steady state that's keeping other steady states steady, and therefore the cell has a homeostatic situation. Example, there's an enzyme complex called sodium-potassium ATPase. It's known as a sodium-potassium pump. You may have seen it. It uses energy from the hydrolysis of ATP to trade sodium ions for potassium ions. It's active transport across the cell membrane so that you have a constant internal concentration of potassium or else you die. So the potassium concentration is in a steady state even though this is an open system in the cell and you have to constantly be using ATP to keep that potassium concentration the same. Here is a diagram of that in the cell. Concentration of the potassium outside the cell is 5 millimolar. So the enzyme needs ATP to work this pumping from the potassium from the lower concentration to the higher concentration, which is the opposite of osmosis. Steady state characteristics: the system is open. The rates at which species enter and leave must be the same. Once established, the concentration doesn't change, and the changes in conditions, like temperature, can establish a new steady state. We're not going to test on any of this. I just don't want you to get steady state and homeostasis and equilibrium consumed. A living organism at equilibrium is, and it doesn't stay there long, it's dead. Now, if the rates of forward and reverse reaction in an equilibrium are the same, and they are, does that make the K's equal? You can probably answer this one already. What will be the ratio of rate forward to rate reverse? Answer, 1. Will that be the same as the ratio of the concentration of product to reactant? Answer, you can probably tell from what you've seen so far. Is it no? Will the ratio of K's change if the temperature does not change? Answer, no. This leads us to the equilibrium constant, and that will be the next video.